Welcome back to Tech Unplugged, everybody. Today, we're diving into the world of databases. And I have to say, I'm really excited about this one.
Databases, yeah. They're kind of the unsung heroes of the tech world, aren't they? So much of what we do online, so many of the apps and services we rely on, all hinge on these systems that store, organize, and manage mountains of data.
Absolutely. And today, we're tackling a big one, Microsoft SQL Server. I mean, this is a system that powers countless businesses, organizations, websites, you name it. There's a lot to unpack.
There is, but don't worry, we're going to break it all down. We'll explore what SQL Server is at its core, the architecture, how it handles data, the tools you use to work with it, and some super important stuff around security and scaling. And just to be clear, we're not going to assume everyone's a database expert here. We'll explain the concepts in a way that makes sense, even if you're just starting out, but we'll also go deep enough to give those of you who already work with databases some real insights.
Perfect. So let's start with the basics. What exactly is Microsoft SQL Server? I mean, we hear the term thrown around, but what's the fundamental definition?
Right. So at its heart, Microsoft SQL Server is a relational database management system. We often shorten that to RDBMS. And what that really means is it's a system for managing data that's organized into tables. You know, like those spreadsheets you see with rows and columns.
Okay, tables, rows, columns. I'm with you so far.
Good. But the crucial part is the relational bit. These tables aren't just isolated islands of data. They can be connected, linked to each other based on relationships between the information they hold. That's what gives us the power and flexibility of a relational database.
So it's not just storing data, it's understanding the connections between different pieces of data.
Exactly. And that's super powerful for maintaining data consistency, avoiding redundancy, and ultimately making your database more efficient and accurate. Like imagine you have a database for customer orders. You might have one table for customer information, another for product information, and another for the orders themselves. Instead of repeating customer details like their address in every single order, you use a unique customer ID to link the tables. Keeps things clean and organized.
Right, and that kind of interconnectedness makes sense, especially when you think about how much data these systems handle. Now, you mentioned SQL Server is built on a client-server architecture. What does that look like in the real world?
Think of it as a conversation. You have applications like the software you use on your computer or phone. These are the clients. They need to access or change data. So they send requests to SQL Server, which acts as the server. It processes those requests and sends back the data or confirms the changes.
So like a constant back and forth, asking questions and getting answers.
Exactly. And this communication can happen on the same machine if your application and database are right next to each other, so to speak. Or it can happen over a network. It could be within your company's network or even across the internet.
Got it. So let's focus on that server side for a bit. What's actually going on inside SQL Server when it gets one of these requests?
Well, it's a pretty sophisticated system, and to understand it better, we usually break it down into three key layers. First, we have the protocol layer.
Protocol layer. Okay, what's happening there?
The protocol layer is all about connectivity. It's like having different doors and pathways for those client applications to come in and talk to SQL Server.
So different ways for them to connect and communicate.
Precisely. And there are several protocols in play. For general communication over networks, you have TCP/IP, a real workhorse. For local access, where everything's on the same machine, shared memory is often used because it's very fast.
So the choice of protocol depends on where the client and server are located.
Exactly. And there are more specialized ones, too. Named pipes are often used within a local network. VIA, that stands for Virtual Interface Adapter, is designed for really high-speed communication between servers, especially in data centers.
It sounds like they've really thought about different use cases and scenarios.
Oh, absolutely. And there's one more that's super important. TDS, the tabular data stream. Think of TDS as the language and format SQL Server uses to package and send data back and forth.
Okay, so the protocol layer sets up the communication channels. Once the request gets through, where does it go next?
It heads straight to the Relational Engine, sometimes called the query processor. This is where the brains of SQL Server reside.
The brain power, that sounds intense.
It is, in a way. It's where SQL Server figures out the best way to take your request, your SQL query, and turn it into action. It involves a few key steps. First up is the CMD parser. This is where your SQL code gets checked for grammar and logic.
So it's like a spell check for SQL, making sure you haven't made any typos or used the wrong commands.
That's a good way to put it. It does a syntax check, making sure you've written your commands correctly, but it also does a semantic check, which is like asking, hey, are you asking for something that exists? Does that table or column you're referencing actually exist in this database?
Right, so you can't just ask for random stuff. It has to be something the database actually knows about.
Exactly. And if there are any errors, the CMD parser will flag them. It also takes your query and creates something called a query tree. This is an internal representation of your request that SQL Server can work with.
Okay, so now SQL Server understands what you're asking. Then what?
Well, then it's time for the optimizer. This is a critically important part. For any command that wants to retrieve or modify data, like select, insert, delete, or update, the optimizer steps in.
Right, those are the commands for getting data out, putting data in, changing data, and removing data.
You got it. And for those commands, the optimizer looks at all the different ways it could actually execute your query. It tries to figure out the most efficient plan possible, takes into account things like how much processing power it needs, memory usage, how many times it has to read from or write to the disk.
So it's like planning the route for a road trip, trying to find the fastest, most fuel-efficient way to get there.
That's a great analogy. And here's an interesting point from the research. Commands that deal with the database's structure, like create table or alter table, they're not optimized in the same way. They're more about defining the framework.
I guess that makes sense. Building the house is a different task than moving furniture around inside it. So once the optimizer has a plan, who's actually in charge of putting it into action?
That's the job of the executor. It takes the execution plan from the optimizer and actually runs it. It interacts with that last layer, the storage engine, to get or change the data.
Okay, so we've got the planner and the doer. What else is going on in the relational engine?
There are a couple of other players worth mentioning. The SQL manager is responsible for handling stored procedures. Those are pre-written, saved chunks of SQL code.
Oh, so instead of writing out a long, complicated query every time, you can just call a stored procedure.
Exactly. And the SQL manager makes sure those procedures are compiled and run efficiently. Then you have the DB manager, or database manager. Its job is to look after all the metadata.
Metadata. What exactly does that mean in this context?
Metadata is essentially data about the database itself. It's the blueprint, the description of its structure, how it's organized, how it can grow, things like that.
So not the data itself, but information about the data.
Exactly. It's like a librarian's card catalog. Tells you where everything is and how to find it.
That makes sense. Okay, so we've got the protocol layer setting up communication, the relational engine figuring out how to execute the request, and the executor actually doing the work. That brings us to that third layer, the storage engine. What's its role in all of this?
The storage engine is all about the nuts and bolts of how data is physically stored and retrieved. It works with the core building blocks of your database: tables, views, rows, and columns. A really important part here is access methods. These act as the bridge between that higher-level relational engine and the lower-level storage components.
The bridge, okay. What are they bridging exactly?
They're connecting the relational engine with the buffer manager and the transaction manager. Their main job is to figure out, hey, is this request asking for data, like a select statement, or is it trying to change the data, like an insert, update, or delete?
So they determine the nature of the request and then direct it to the appropriate handler.
Got it.
Now, tell me about that buffer manager. What's its function?
The buffer manager is all about making things run fast. It's the master of memory management in SQL Server.
Memory, that's RAM, right? So how does it use RAM to speed things up?
It has a couple of really clever tricks. One is managing the plan cache. Remember how the optimizer came up with that super efficient plan for executing your query? Well, those plans get stored in the plan cache. So when a new query comes in, the buffer manager checks, hey, do we already have a plan for this? If they do, it's like, boom, let's reuse that plan. It's called a soft parse, and it saves a ton of processing time.
Oh, so instead of recalculating everything every time, it can just pull out a pre-made plan. That's brilliant.
It is, but if there's no existing plan, then the buffer manager has to go through a hard parse and generate a new one, and that's where things can get a bit slower. The buffer manager is also responsible for the actual data pages that are held in memory. This is called data parsing. It basically creates a cache for frequently accessed data.
Like a shortcut, so SQL Server doesn't have to go all the way back to the disk every time it needs that data.
Precisely. It moves chunks of data, called pages, between memory and disk storage as needed. And this whole caching mechanism can dramatically speed up queries, especially for those bits of data that are accessed all the time.
Keeping frequently used information close at hand. Okay, and then the last key part of the storage engine is the transaction manager, right? What does it do?
The transaction manager is all about ensuring that your data stays consistent and reliable, especially when you're making changes, with those non-select statements. And it relies on two really important subcomponents. First, the log manager. This keeps a meticulous record of every single change made to the database.
Every single change, wow. Like a detailed history log.
Exactly. And this log is absolutely crucial for recovering the database if there's a crash or a failure. Then there's the lock manager. It's stepped in when you have multiple users trying to change the same data at the same time.
Oh, that sounds like a recipe for chaos.
It could be, but that's where the lock manager comes in. It uses locking mechanisms to prevent conflicts and make sure everything happens in a safe and orderly way. This ensures those famous SID properties of database transactions.
AC top properties, I've heard that before, but could you remind me what they are?
Of course. ACID stands for atomicity, consistency, isolation, and durability. Atomicity means that a transaction is all or nothing. Either all parts of it complete successfully or none of them do. No half-finished transactions messing things up. Consistency ensures that the database always stays in a valid state. No broken rules or invalid data.
So the database always makes sense, even if multiple things are happening at the same time.
Exactly. Isolation means that transactions are protected from each other. It's like each transaction is happening in its own little bubble so they don't interfere with each other's work. And durability guarantees that once a transaction is complete, it's permanently recorded. No going back, it's done, it's safe.
That makes sense.
Okay.
Reliability and consistency are super important, especially when you're dealing with crucial business data. Now, one of the sources mentioned something called SQL OS. Is that part of the storage engine?
It's actually a bit lower level than that. SQL OS stands for SQL Server Operating System. It's a foundational layer that provides those essential operating system-like services that the Relational Engine and Storage Engine depend on.
Operating system-like. So is it a separate operating system running inside SQL Server?
Not quite a full-blown operating system, but it provides services like memory allocation, handling input-output operations with the disks, things like that.
Okay, so it's like an internal operating system layer.
Exactly. It takes care of the low-level stuff so the higher-level engines can focus on managing data.
That makes sense.
Yeah.
All right, so we've got a pretty good grasp on the underlying architecture. Let's move on to how SQL Server actually stores and manages our data. We've talked about tables, rows, and columns, but what's the physical storage like on disk?
Right, so on the logical level, you organize your data into databases. And a database is essentially a collection of tables that are related to each other in some way. Each table has a defined structure, with columns representing different attributes of the data and data types specifying what kind of data each column can hold.
Like text, numbers, dates, things like that.
Exactly. Common data types are int for integers, and varchar for strings of text, date for, well, dates. And to ensure the data is consistent and makes sense, you can enforce rules using constraints.
Constraints? That sounds kind of restrictive.
They are, in a good way. Constraints help maintain data integrity. For example, a primary key constraint enforces the uniqueness of each row in a table. So no two customers can have the same customer ID. And a foreign key constraint creates those relationships between tables, like ensuring that every order is linked to a valid customer ID.
So constraints are like guardrails. They keep the data organized and prevent mistakes from creeping in.
That's a great way to think about it. And all this logical organization, how does that translate into the physical files on your hard drive? Well, SQL Server breaks things down into 8 KB chunks called pages.
Pages, okay. And all the data is stored in these pages.
Yes, and for better management, these pages are grouped into extents, which are 8 contiguous pages. Now, the actual data for your tables lives in data files. The primary data file has a .ndf extension, and you can have additional secondary data files with a .ndf extension.
So .ndf for the main data, .ndf for any extra data files. What about keeping track of all the changes that are made?
That's where the transaction log files come in. They have a .ldf extension, and they record every single change to the database.
That's important, right, in case you need to roll back a change or recover from a crash?
Absolutely vital. These log files are your safety net, and then there's tempdb. That's a special system database that SQL Server uses for temporary storage during query processing.
Like a scratch pad.
Precisely. It holds intermediate results, temporary tables, things like that. Now, when we talk about managing data, a crucial aspect is performance. We want those queries to run quickly, especially when dealing with large amounts of data. That's where indexes come into play, right?
Indexes, yes. Those are like the lookup tables in the back of a book, right?
That's a good analogy. Indexes help SQL Server find the data it needs quickly without having to scan the entire table. SQL Server uses two main types of indexes, clustered and non-clustered. Now, a table can only have one clustered index.
One per table. Okay. What makes it clustered?
A clustered index actually physically reorders the rows in the table on disk based on the index key you choose.
So it's not just a separate index, it changes the actual physical order of the data.
Exactly. Think of it like arranging a library by author's last name. The books themselves are physically ordered that way.
And non-clustered indexes, how are they different?
Non-clustered indexes create a separate structure, a kind of lookup table that has a copy of the index key columns and a pointer to the actual row in the table. You can have multiple non-clustered indexes on a single table.
So like having multiple indexes in a book, one by author, one by title, one by subject.
Exactly. It gives you different ways to quickly find the information you need. Now imagine you're dealing with massive tables, millions or even billions of rows. How do you manage that effectively? That's where data partitioning comes in.
Data partitioning, that sounds interesting. What is it?
It's a way to divide a very large table into smaller, more manageable chunks called partitions. And you can partition the data in different ways. Horizontal partitioning splits the table based on rows. Like maybe you partition a sales table by year, so all the 2023 sales go in one partition, 2022 sales in another, and so on.
I see. So instead of one giant table, you have smaller, more focused tables.
Exactly. And that can make queries much faster because SQL Server often only needs to work with the relevant partitions, not the entire massive table. There's also vertical partitioning, where you split the table based on columns, although that's less common in SQL Server. And then you can partition based on file groups, which lets you control where different partitions are physically stored on disk.
So like organizing a library into different sections, different floors maybe, to make it easier to find books and keep things organized.
A perfect analogy. Now, once you've got your data stored and organized, the next question is, how do you actually interact with SQL Server? How do you tell it what to do?
Right, we need to be able to talk to it, ask it questions, tell it to do things.
And the language we use for that is Transact SQL, usually shortened to T-SQL. It's Microsoft's extended version of the standard SQL language, and it includes a lot of extra features and capabilities that are specific to SQL Server.
So T-SQL is our way of communicating with SQL Server. And what tools do we use to write and execute T-SQL?
There are several popular tools, each with its own strength. One of the most commonly used is SQL Server Management Studio, or SSMS. It's a very powerful graphical tool for managing and administering every aspect of SQL Server.
So not just writing queries, but managing the entire database system.
Exactly. And it includes a robust query editor for writing and running your T-SQL code. If you prefer a more lightweight, cross-platform tool, Microsoft offers Azure Data Studio. It works with SQL Server and other database systems too.
So a bit more flexible in terms of the types of databases it supports. What about for developers who work within the Visual Studio environment?
For them, there's SQL Server Data Tools, or SSDT. It integrates database development directly into Visual Studio, which can be a real time saver.
Keeps everything in one place. And for those who prefer a command line interface.
There's the trusty SQL AME utility. It's a command line tool that lets you interact with SQL Server directly from the terminal or command prompt.
So there are tools for every preference and workflow. Now, what about when we have queries that we need to run over and over again? Is there a way to save those within the database itself?
Absolutely. That's where stored procedures come in. They're blocks of T-SQL code that you can save and store directly within the SQL Server database.
So like pre-made recipes that you can just pull out and use whenever you need them?
Perfect analogy. And they offer several advantages. First, they're often compiled ahead of time on the server so they can run faster. They also reduce network traffic because you're just sending the name of the stored procedure instead of the entire query every time. And they can be great for security too.
How so?
Well, you can grant users permission to run a stored procedure without giving them direct access to the underlying tables. It's a way to control what they can do and protect sensitive data. Another important concept is views.
I've heard of views, but I'm not exactly sure what they are.
A view is essentially a virtual table. It doesn't actually store any data itself, but it represents a predefined query.
So it's like a window into the real data, showing a specific perspective.
Exactly. And views can be really useful for simplifying complex data structures or for creating custom perspectives on the data for reporting or analysis. They also play a role in security by controlling which parts of the data users can see.
So views for creating focused, customized perspectives on the data.
Got it.
What about triggers? They sound like they're actions that happen automatically.
They are. Triggers are special kinds of stored procedures that get executed automatically when certain events happen in the database. like inserting a new row into a table, updating an existing row, or deleting a row.
So it's like setting up a chain reaction. If this happens, then do that.
That's a good way to think about it.
Oh, yeah.
And triggers are often used for things like enforcing business rules, auditing changes to data, or maintaining consistency across related tables.
So they can be used for all sorts of behind-the-scenes tasks. And what about common table expressions? They sound a bit more advanced.
CTEs, as we usually call them, are really helpful for writing complex queries in a more readable and manageable way. They're temporary, named result sets that you define within a single query.
Temporary result set. So they're like virtual tables that exist only within the scope of that one query.
Exactly. It's like creating a temporary view just for that particular query.
That sounds like a powerful way to break down complex logic into smaller, easier to understand chunks.
Absolutely. Now, before we move on, there were some specific examples of T-SQL operations in the information you provided. Want to take a quick look at those?
Yeah, let's see some of these concepts in action.
Okay, so let's say we want to create a new table called employee with columns for ID, name, department ID, and hire date. We would use the create table statement.
And that statement would define the name of each column and its data type.
Right. Then, to speed up searches, we'd probably want to create indexes. A clustered index on the ID column, because that's likely our primary identifier, and maybe a non-clustered index on the name column. We'd use the create clustered index and create non-clustered index statements for those.
And how do we actually populate this new table with data?
To add new employees, we'd use the insert into statement, specifying the values for each column. And if we needed to add a new column, like a salary column, we could use the alter table command.
And to update existing information, like giving someone a raise.
That's where the update statement comes in. You use a where clause to specify which rows you want to change. And if we wanted to change the table's name from employee to staff, we could use the exec spree name stored procedure.
What about removing data from the table?
For that, we have a few options. To remove specific rows, you use the delete from statement with a where clause. If you want to delete all the rows but keep the table itself, you can use the truncate table command. It's usually faster than deleting individual rows because it doesn't log every single deletion.
If you wanted to get rid of the entire table data and all.
Then you would use the drop table statement. Poof, it's gone.
Okay, that covers the basics of creating, modifying, and deleting data. What about those cursors we talked about earlier?
Cursors are a way to process data row by row, sequentially. You declare a cursor, open it, then you fetch the next row, do something with it, and repeat until you've gone through all the rows.
So it's like taking a fine-toothed comb and going through each row individually.
Exactly. Now, there are usually more efficient ways to process large data sets in SQL, but sometimes you need that level of fine-grained control.
What about examples for creating views and triggers?
To create a view, you use the create viewW statement, followed by the as keyword, and then the select query that defines the view. Triggers are a bit more involved. You use the create trigger statement, specify the table, the event that triggers it, like after insert, and then the T-SQL code you want to execute.
And those common table expressions or CTEs and all the different types of joins.
For a CTE, you use the with keyword, give the CTE a name, and then write the query that defines it. Then you can refer to that named result set in your main query. Joins are all about combining data from multiple tables.
Right, like pulling together customer information from one table and their order history from another.
Exactly. There are several types of joins. Inner join, left join, right join, self join, and cross join, each with different rules for how rows are combined.
A whole family of joins. And lastly, those ranking functions in T-SQL.
Ranking functions are super useful for analyzing data based on relative positions. Row number assigns a unique number to each row in a result set. Rank and denser rank assign ranks based on a specified order, but handled differently.
Okay, that was a whirlwind tour of T-SQL, but really helpful to see it in action. Now, let's think about what happens when our database grows. When we have more data, more users, more demands on the system, how do we make sure SQL Server keeps up?
That's a critical question, and it brings us to the topics of scaling and availability. As your needs grow, you need to be able to handle that increased load.
Right, because a slow database can be a real bottleneck. So how do we make SQL Server faster and more robust?
Well, there are two main approaches to scaling. Vertical scaling, often called scaling up, involves boosting the resources of your existing server. Think adding more CPU power, more RAM, faster disks. Horizontal scaling, or scaling out, involves spreading the data and workload across multiple SQL Server instances.
So vertical is making one machine more powerful. Horizontal is using multiple machines.
Exactly. And on the horizontal side, there are a few common techniques. Sharding involves dividing your data across multiple databases, often based on some specific criteria. Replication involves maintaining copies of your data on multiple servers. And distributed partition views let you query data that's spread across multiple databases as if it were one big table.
Lots of options for handling growth. But what about keeping the database up and running? That's got to be a top priority.
Absolutely. High availability is essential. SQL Server provides some powerful features for minimizing downtime. Always on. Availability groups let you create sets of primary and secondary database replicas. If the primary server goes down, a secondary replica can automatically take over. It's like having a backup quarterback ready to step in.
So it's about ensuring continuous operation, even if there's a failure.
Exactly. Another option is log shipping. It involves backing up the transaction logs from the primary server and restoring them on a secondary server. It's not automatic failover like always on, but it's a good solution for disaster recovery.
So, always on for instant failover, log shipping for recovering from a disaster. Both important. All right, let's talk about another huge topic. Security. I mean, databases often hold sensitive information, so how do we keep it safe?
Security is a paramount concern in the world of databases. And SQL Server provides a really comprehensive set of features to protect your data from a wide range of threats.
Threats like what? What are the main things we're trying to protect against?
Well, you have unauthorized access, people trying to get into the system who shouldn't be there. You have SQL injection attacks, which are a way of exploiting vulnerabilities in application code to gain access to the database. You have malware, you have data leaks, and even insider threats where people within your organization misuse their access.
So a whole spectrum of risks. What are the first lines of defense?
The very first step is authentication. This is all about verifying the identity of anyone who tries to connect to SQL Server. SQL Server supports a couple of key mechanisms. Windows authentication uses your Windows domain credentials, so it leverages Active Directory.
So if you're logged into your company network, you can use those same credentials to access the database.
Exactly. And it simplifies things for users because they don't need separate usernames and passwords. Then there's SQL Server Authentication, which manages usernames and passwords directly within SQL Server. And you can configure mixed mode authentication to allow both. For cloud deployments with Azure SQL Database, Azure AD Authentication is also available.
So different authentication methods for different environments and needs.
Yeah.
But authentication just gets you in the door, right?
Yeah.
How do we control what people can actually do once they're inside the database?
That's where authorization comes in. This is about defining permissions and access control.
Right, because not everyone should be able to see everything or change anything they want.
Precisely. Authorization involves a few key elements. Principals, which are the security identities, like logins and users. Securables, which are the objects within SQL Server that you want to protect, like databases, tables, stored procedures. And permissions, which are the specific rights that you grant to those principals.
Okay, so it's about who's allowed to do what.
Exactly. And to make this whole process easier to manage, SQL Server uses something called Role-Based Access Control, or RBAC. It allows you to group users into roles, and those roles have predefined sets of permissions. There are built-in server roles and database roles, and you can also create your own custom roles.
So instead of managing permissions for each individual user, you can just assign them to a role.
Exactly. It's much more efficient. And a key principle here is something called the principle of least privilege.
Principle of least privilege. What's that all about?
It means you should only grant users the bare minimum permissions they need to do their job. No more, no less. It's a fundamental security best practice.
Makes sense. Limit the potential damage if someone's credentials are compromised. Now, what about protecting the data itself? I mean, not just who can access it, but making sure the data itself is secure, both when it's stored on disk and when it's being transmitted over the network.
That's where encryption comes in. SQL Server has several powerful encryption options. One is transparent data encryption, or TDE.
Transparent data encryption. Okay. What does that do?
TDE encrypts the entire database while it's at rest, meaning stored on disk. So if someone steals the physical hard drive or gets access to the storage, the data is still protected.